this session. In this session, I'm going to treat numerical solutions to Fredholm's integral equation. As in our previous video, we look at the numerical solution to Fredholm's integral equation. But in this session, I'm going to consider examples. An example under this Fredholm's solutions, numerical solutions to Fredholm's equation. And it's saying that solve the following using any quadrature numerical method. Y of x equal to 1 plus integral from 0 to 1 st y of t dt. Use any convenient step size h. So solution. Let's consider our integral equations, which is y of s equal to 1 plus integral from 0 to 1 st y of t dt. Now s is a constant here because the integral is respect to t, so we can factorize the s out. So after factoring this s out, now our equation becomes this: y of s equal to 1 plus s integral from 0 to 1 y of t y of t dt. Now the interval we are going to integrate is between 0 and 1. Since we are using numerical integration, that is the quadrature, that we need to discretize this point and select our convenience or step size h. And so we have the interval to be between 0, 1. Now, let's select a step size such that if you sum from the starting of the loop to what, you get 1. So let's select it to be what, 0.5. And the smaller the step size, the more accurate the solution becomes. So let's discretize this point. We're having 0 here, then 1. If you add 0.5 to 0, you're going to get 0.5. Now 0.5 to 0.5, you're going to get what? 1. Now let's name here to be our S0 and here to be S1 and here also to be S2. The last index here is what? 2, and that is the quadrature loop, which is giving us 0 si, where I running from 0 to what? N. This time, yes, 0, 1, 2. So our n here is what? 2. So I'm going to sum the nodes up to 2. That's why I'm having the here to be S0, S1, S2. Now let's apply numerical quadrature on this Fredholm's integral equation. And in our previous video, we noticed that if you are giving an integral, let's say I to be equal to integral from a to b f of s ds. We said it's by numerical integrations. We said it's equal to a certain v of f plus e of f. And we said the e of f is a truncated error. So if you drop the truncated error, this is the same as this will be approximated to the vf. And we had our vf to be equal to summation of ai and the functional values of what? I run from 0 to n. But this time around, our n is what? Equal to 2. So I run from what? 0 to what? 2, which is the same as. So if I is 0, I'm going to have a naught, then the functional value of what? A naught. plus I is 1, we would have A1 times the fractional value of what? A1 plus if I is 2, I'm going to have A2 times the fractional value of A2. Now, we're having v of f to be this. And let's consider the Fredholm integral equation. The integral side, which is from 0 to 1, ty of t dt. Wait, this implies that integral from 0 to 1, ty of t dt, which will be the same as, that means the f here is the same as ty of what? T. So the same as v of ty of t, which will be equal to summation of I to be equal to 0 to n, then ti, then y of what? Ti. Since there's an s here, there's an s here, we are going to use an index for, we are going to use I for this. Then let's use j for the index. Let's change the indexes here to j's. So j equal to 0 for 0, which is 1 from towards n. We said the n is equal to 2. So this n becomes 2. So if you sum this, if you open this side, I'm going to get, when j is 0, I'm going to get t naught, y of t naught, plus, then when j is equal to 1, I'm going to have t1, y t1, plus, when j gets to 2, I'm going to have t2, y t2. And the question said we should use what? Any quadrature numerical method. And the quadrature techniques we considered the last time were trapezoidal rule, Simpson's rule, and Simpson's 3/8. So in this particular example, let's consider Simpson's 1/3 rule. Simpson's 1/3 rule. He says that whenever you are given an integral, let's say integral from a to b f of s ds is equal to, then the step size divided by 3. Then the first functional value, which is f naught, plus 4 times index. The index here, when it is odd, you multiply it by 4. So let's say 1 plus 2. When it is even, you multiply it by 2 plus dot until you get to your n term plus fn. Since we are dealing with what? J to be equal to 0 to n, this implies that this here becomes h over 3. Then the first entry becomes f naught, followed by f1, then f2. So f1 is what? Odd. So here becomes 4 f1 plus the n term, which is what? f2. Now we are going to put this vein of ty of t into this. So this becomes v ty of t becomes, we are placing it into the Simpson's 1/3. So it becomes h over 3 into bracket. Then the t naught, we are having t naught, y t naught, and what? t1, y t1, then t2, y t2. So we are placing it into the Simpson's 1/3. We are going to have our first entry to be t naught, y t naught, plus the next term, which is 4 times t1 yt1, because you're having an index of 1, which is odd, so you multiply this term by odd 4. You have our last term to be t2, so t2 times yt2. So this is our last term. Now t naught and s naught are the same, and t1, t naught and s naught are the same. So we have 0 for t naught, and t1 and s12 are the same. We have 0.5. So here becomes 0.5. And t2 and s2 are also the same. We are having t2 to be, which is equal to 1. Now let's substitute this into what? Our v. So v of t, yt, becomes the step size, which is h divided by 3. Then t naught is 0. So 0 times y of 0 plus this 4, and the t1 is 0.5. So 4 into bracket 0.5. Then y of 0.5 plus t2 is 1. So here becomes plus 1 times what? y1. y1. 0 times y of 0 becomes what? The same as 0. We have our step size to be 0.5. So you can just substitute into our v t y of t. So here becomes 0.5 divided by 3. So this is 0. So here becomes 4 times 0.5 gives me 2. So here is 2 y of 0.5 plus y1. And here is the same as 1 out of 6, because 0.5 is the same as 1 over 2. So 1 over 2 times 1 over 3 will give 1 out of 6. So this, now we have this 2 times y of 0.5, then plus y1. Now we are able to estimate this integral. I'm going to substitute this integral into what? Our Fredholm's integral equation. So our y of x, and let's add index to the x because it becomes an iterative solution. So our first index, let's say si to be equal to 1 plus si. Then let's substitute the whole of what? The v of what? T, because we are saying that that's the integral of what? Integral from 0 to 1 y of t dt, which is the same as the v of what? T yt. So si into bracket 1 out of 6, the big bracket 2 times y of 0.5 plus y1. So here is the same as y si equal to 1, then you can just do it plus si divided by 6 into bracket 2 of what? Y of 0.5 plus y1. Now you need to look for our iterative solution, and our iterative solution needs to end at what? 2. Since we have our n to be equal to 2. So first, for I equal to 0, for I equal to be 0, I'm going to have what? Y s naught be equal to 1 plus s naught divided by 6 into bracket 2 of y of 0.5 plus y1. And we had our s naught to be 0. Our s naught is 0. That which means that the whole of this side will go off. So y of 0 to be equal to, so if you put 1 plus or 0 times the whole of this term also goes to 0. So y of 0 becomes what? 1. So this is our first iterative solution. So y of 0 is equal to what? 1. The next iterative solution, when I moves to 1, that means I equal to 1. I'm going to have ys1 which is equal to what? 1 plus. So I'm going to have s1 divided by 6. Bracket 2y of what? 0.5 plus y1. And we had our y1 to be 0.5. So let's substitute it into this equation. We are going to have y of 0.5 to be equal to 1 plus 0.5 divided by 6 bracket 2. Then my what? Y of 0.5 plus y1. And let's simplify this. I'm going to have here to be y of 0.5 to be equal to 1. Here becomes 0.5 divided by 6 becomes 1 over 12 plus plus 1 over 12 bracket 2 of y of 0.5 plus y of 1. Now let's open up this bracket. So we are going to have y of 0.5 to be equal to 1. 12 times 2 becomes what? 1 out of 6. 2 plus 1 out of 6 y of 0.5 plus 1 out of 12. 12 times y1. Now let's send the unknowns to what? This side. So I'm going to have y of 0.5 minus 1 out of 6 y of 0.5 minus 1 out of 12 y of 1 to be equal to this 1. And y of 0.5 minus 1 out of 6 y of 0.5 is same as 5 out of 6 y of what? 0.5 and minus what? 1 out of 12 y1 to be equal to 1. Let's take here as our equation 1. We need to solve this unknown. Y of 0.5. The solution estimate as 0.5 and the solution estimate as y of 1. So let's take here as our equation 1. When I gets to 2, here we have y of what? S2. Y of S2 to be equal to this one plus S2 divided by 6 into bracket. We are going to have what? These entries, which is 2 of what? Y of 0.5 plus what? Y1. and we had our S2 to be equal to 1. That's the N, the Sn, that's the S2. So we are going to have here to be y1 to be equal to 1 plus 1 out of 6. Then 2y of 0.5 plus this y1. Now let's simplify this equation. I'm going to have here to be y1 to be equal to 1 plus 1 out of 6 times 2 will give me what? 1 out of 3. Y of 0.5. 1 out of 6 times this, I'll get plus 1 out of 6 y1. So let's group items. Let's send the unknowns to the other side of the equation. I'm going to have minus 1 out of 3 y of 0.5 plus y1 minus 1 out of 6 y of 1 to be equal to 1. So this is the same as minus 1 out of 3 y of 0.5. Then y1 minus what? 1 out of 6 y1 becomes 5 out of 6 y1. And let's name here as our equation 2. Now to solve for this unknowns, y of 0.5 and y at 1, you solve equation 1 and equation 2 simultaneously. And so let's use Clearance rule. Let's first place it in a matrix notation. So in a matrix notation, matrix representation, we have here to be 5 out of 6, then minus of 1 out of 12. So the first entry becomes 1 out of 6. 5 out of 6. Then minus 1 out of 12. Then we have here also to be minus 1 out of 3 and 5 out of 6. And 5 out of 6. Then the unknowns comes to this side. Which is equal to 1. And the other side 2 is equal to 1. Now, by Clearance rule, you need to find for the determinant of this matrix. So let D to be equal to determinant of 5 out of 6, then minus 1 out of 12, then minus 1 out of 3, 5 out of 6. This is the same as 5 over 6 times 5 over 6, then minus into bracket minus 1 out of 3 times minus 1 out of 12. 5, so here becomes 5 times 5 is 25 and 6 is 86. So 25 out of what? 36 minus. So here becomes minus 1 times minus 1 get 1 divided by 3. 12 is the same as 36. So 25 over 36 minus 1 out of 36. I'm going to get 24 out of 36 as the determinant of what? This matrix. Now to find for your y of 0.5, the same as I want to name a certain matrix which is the same as d1 over this determinant, and y1 I'm going to name a certain determinant as d2 over what? D. And let's find for our d1 and d2. So our d1 the same as we just select these entries and put these entries into this to have our determinant of what? D1. So I'm going to have 1, 1, then minus 1 out of 12, then 5 out of 6. So then the determinant sign. So 1 times what? 1 out of 6. I'm going to get 5 out of 6. I'm going to get 5 out of 6. So minus into bracket. 1 times I'm going to get minus of 1 out of what? 12. So it is the same as 5 out of 6 plus 1 out of 12. Which will be equal to, the LCM here is 12. Then 6 going to add 2 times. So 2 times 5 is 10. So plus 1. I'm going to get 11 out of 12 for D1. And our D2. Our D2 becomes, we delete these entries and bring this one to the side and find the determinant of that. So we are going to have 5 out of 6, then minus 1 out of 3, then these entries 1, 1. 5 out of 6 times 1 is the same as 5 out of 6. Minus into bracket. Minus 1 over 3 times this. You still get minus 1 over 3. Which will be equal to 5 out of 6 plus 1 out of 3. So the LCM is 6. Here becomes 6 going to itself 1. So 1 times 5, we're going to get 5 here. So this going to this 2 times this one is equal to what? 2. We're going to get 7 out of what? 6. So having our D1 and D2, now you can easily compete for our y of 0.5 and y of 1. So our y of 0.5, which was given as D1 over D, and our D1 is given as 11 out of 12, and D is given as 24 out of what? 36. So 11 out of 12 divided by 24 out of 36. Now if you solve this, I'm going to have 11 out of 12 times, then you interchange this reciprocal of it, we got 36 out of 24. This one cancels itself 1 and cancel this one. 36 3 times. 3 cancels itself 1 and cancel 24 8 times. So I'm going to have 11 out of 8. And our y1 is the same as d2 over d. Our d2 is the same as 7 out of 6. So we're going to have 7 out of 6 divided by 24 out of 36. So this is the same as, if we complete the whole of it, we're going to get 7 out of 4. Now, we have our y naught to be equal to 1 and y of 0.5 to be equal to 11 out of 8 and y1 to be equal to 7 out of 4. So, from this side, to find for the unknown, for the approximate solution to the integral equation, let's drop the index, the i's. So we're going to have y of s to be equal to 1 plus s over 6 to bracket wey is same as 2y of 0.5 plus y1. Now let's substitute this y of 0 to be equal to 1, this and this into this equation. I'm going to have y of s to be equal to 1 plus s over 6 into bracket 2 times 11 over 8 plus y1, which is the same as 7 over 4. So here becomes 1 plus s over 6, the same as 11 out of 4 plus 7 out of 4. So we're going to have 1 plus s divided by 6. Then here becomes 7 plus 11 plus 7 gives me 18 divided by 4. And this 6 will cancel 18 3 times. So here the whole of this becomes 1 plus 3 out of what? 4 s. Where is that? Y of s is the same as 1 plus 3 over 4s. So this is the approximated solution to the Fredholm's integral equation given in the question. So anytime you are given a Fredholm's integral equation to solve using numerical solutions, that's the quadrature format. So this is the same format you need to pass through to get the approximate solution.